Hello guys, so welcome back to the LeRobot SO101 series. So in the previous two videos, we had discussed about the hardware SO101 Arm and the various ways to collect dataset, in which we focused on VR based teleoperation. So now the second, in this video we'll go through some more other state of the art dataset collection methods, and also deep dive into the LeRobot website and what all policies they have provided us, and also we'll try to look at the algorithms in much more detail. So first we'll start with the dataset collection method, which is called UMI, and it stands for Universal Manipulation Interface. So as you can see, here you can see a robotic gripper which an person is using it to collect data set. So here you can see this is the gripper which has a camera on it. So this is a GoPro camera, and there are two mirrors on the gripper which make it a three camera setup. So basically you have a GoPro overhead camera or a global camera and two local cameras which are replicated using a mirror. So as you can see, an human is teleoperating, so he's doing some task collecting data set. So what is a data set? So it consists of your camera feed, three camera feeds, and also the end effector position, all recorded together. So as you can see, after you collect data set and you train a policy, you can see how it's working in real life. So you can see the right top corners where it's mounted on a UR5 robotic arm. So here you can see a sample task where they're trying to fold some clothes, and you can see one more task where it's picking up objects and placing it in the box. So this technology was developed by Stanford and it's fully open sourced. Also all the design files, so you can see you have the code is available, and also how you can assemble this gripper, it's fully open source. So yeah, this is about UMI. You guys can check out, and we'll also attach all the links in the description of the video. The next setup is called ALOHA. So it stands for low cost hardware setup, and it is also developed for this type of imitation learning task. So in this setup, I will give you a brief overview. So here you can see there are four arms. So there are two leader, two follower. It's a similar setup which we had shown you in the previous video using the SO101 arm, but these arms are a bit more advanced and you can say a bit more in precision. So it's an industrial arm. You can see here. So the sensors here are, this is a depth camera which is mounted on the gripper, so which you can see here, and this is the whole setup where you have totally four cameras. So two here, one on this arm, one on the second arm, and two on the base. So the setup is four cameras and your four arms, where two arms are the leader, so which the person will operate. So you can see the video here. So this is the setup, and it's developed with via Google DeepMind company. You might have heard of it. So here you can see a person is teleoperating it, where he's moving the leader arm and the follower arm is also replicating the same action. So you can see here, these are the complex tasks which they are trying to achieve. So this is a can pouring in a mug. So these are all the complicated tasks, and this is all done via collecting data set and then training imitation learning policy. Yeah, so this is the ALOHA setup, and as you can see there is ALOHA 2. So this is a second version of this setup. Previously there was ALOHA V1 which just used normal RGB cameras, but in this V2 they have upgraded it to a depth camera setup for more accuracy and other parameters. So this was all about the dataset collection methods. So we had looked through VR based method, which is very intuitive for anyone to use. Then the second method we looked was the UMI, and the third one, this is not actually a method but it's a whole complete setup which is also used by many people across the world. Now we'll go through the major part of this video, which is the LeRobot ecosystem. So I guess you might have seen in the previous video about the arms. So this is the arm which we had used, the SO101 arm. And this is the main website of LeRobot. So you have to just search LeRobot SO101 on your Google and you will land to this website, the first link. So as you can see in this website, you have various things. So you have a get started section, a tutorial section. So once you assemble the arm, you will first need to install your, you just follow these instructions. This will install your LeRobot workspace in your PC. So yeah, so there are all the instructions given. You can follow it step by step. So there is two methods. One is via Conda, or you can use UV package manager. Then the major part is the policies part, which we are going to look in this video. So here you can see in this section called policies, we have mentioned all the algorithms or policies which are provided by the LeRobot ecosystem, which you can directly use. So the first policy, which is called ACT. So ACT stands for action chunking with transformers. So this was the initial breakthrough in the imitation learning ecosystem. So as you know, the word imitation learning, what does it mean? So basically you do something and a robot or any other thing just replicates it. So the most fundamental algorithm for imitation learning is called behavior cloning. So basically assume I move my arm from point A to point B. I show it and the robot should also just replicate it. That was the most simplest method. The next thing which came is called ACT, and it's called action chunking with transformers. So in this, what it does, it's a smarter method to do. So your input is basically your camera feed and your joint states. Joint states means all the joint angle of each joints. So your input is joint states and camera feed. Camera is, again, as we discussed, one camera on the end effector and one global camera. So two camera plus your joint states, that is an input, and your final output is an action chunk. So what does a chunk mean? Action chunk is like, so it's a collection of actions. So say if I have my input camera 1, C1 and state 1, it will predict action 1 to say some 10. So A1 to A10 will be predicted in a single time step. So that is called action chunk. So this is more robust because it is trying to predict the future actions. Yeah, so that is action chunk. And you can also go through the official paper, which is just linked here. So yeah, this is the official research paper by, yeah, this is the ACT's official research paper. And you can see here, as I discussed before, they are also using the same ALOHA setup, which I had discussed before. And this is the main algorithm. So I will just explain it in a very brief manner, not in detail. This you can look through by yourself. We'll attach all the links. So yeah, here you can see it's basically conditional variation autoencoder method. So this is called a variational autoencoder, where we have an encoder and then we have finally a decoder. So also, as you know, I have been using the word policy and training. So first I'll explain what's that. So in the previous video, we learned how to collect data set. So what will we do after we collect a data set? So after we collect a data set, there's a process called training. What we train? We train basically an encoder in this case. So you can see your input is the joint angles and the joints, current joints, and the dataset's action sequence. This is fed to the encoder, and then we get a Z style variable. So we won't go that much detail, but it just gives you a probability distribution of how you moved your arm. So basically, so say my task is to pick a box and place it in a, what do you call, a can. So there are many ways I can do it. I can approach it like this. I can approach it in this manner. So a human can do various methods. So this Z style variable captures the whole distribution or the multimodality into this Z variable. It's a probability distribution. So while training, it trains and this Z variable is learned by the policy. Then you can see this part, the second part. Yeah, yes. So this part you can see, this is the camera feed. So you can see 1, 2, 3, 4. This is the camera input. This is fed here. Then we have again the joint states. This is coming from the arm directly. Then we have a Z style variable, again which was used here after training. So after training, when you feed this, and finally you get the action sequence. So there are two steps. One is training, where the policy learns what to predict, and then there is another step called inference. So after you train, to see the results of your policy, how it's performing, you do this part where you feed the camera input and joints, and then it returns action sequence. Yeah. And if you want to read more further about the algorithm, here it's given, you can go through it. So it's a bit math heavy, but I would suggest everyone who is interested in learning more about vision language action models or imitation learning, you can go through it. Yeah. Yeah. So as we had discussed about ACT, which was action chunking transformer, the next breakthrough in the imitation learning field was termed as VLA, which stands for Vision Language Action Model. We also have a live session conducted on VLA. You can go through it to get a brief overview. So in this, we'll talk about a specific VLA, which is called smolVLA, which is just developed for edge robotic platform or running on say a smaller GPU with less VRAM. So generally, VLAs have a thing called parameters, which are in terms of billions. So the first VLA which was made was called OpenVLA. Then Google made its own RTVLA. There are so many VLAs, but they are all need a lot heavy compute, say 40 GB VRAM, 50 GB VRAM to just train. And for inference also, you need a very big GPU. But this is the first VLA which is just 1.6 billion parameters, and it's termed as smolVLA because it's shrinked in size and half of the layers have been removed. So it was termed as smolVLA. So as you can see, this is a open source thing, and it's there on LeRobot, which you can directly use using the collector dataset. So the LeRobot usually follows a fixed dataset format called a LeRobot dataset format, which is applicable for all the policies which is listed here, which is common to all. So you just install the smolVLA package, and then there are commands also mentioned here to train the policy. So here you can see LeRobot train. There are many parameters inside the training one. One is batch size, then there are steps and various others. We won't go in much detail, but the brief overview is that in VLA, the input is vision input, which is from your cameras, is same as in ACT. Then there is a language input. So that is the main key difference. The language input is called a task description. So why we need a VLA? Why can't we just use ACT or something like diffusion policy? The major use is to generalize. So if I say I want to do multiple tasks with just one policy, so if I had a task of picking and placing, then I have a task of say folding clothes. If I want a single model to do it, then that's the answer for VLA. So VLA can generalize as it has a task description parameter. So you just give the prompt, say fold the cloth. So now it will know what task to do, and then it will assign its learned actions. So yeah, the input is vision, language, and the action from your dataset. Action is the joint states. So if you have two arms, it's 12 joint states. If it's a single arm, then it's 6 joint states. So you take it in that as input, then it's passed to a thing called VLM. So you might have heard of LLMs. So you guys might have been using ChatGPT, Claude, and other LLMs a lot these days. So VLM is just a vision layer added. So you have a language model plus a vision part. So there are many examples of VLM like PalyGemma, which is used by Pi0. So you can see here Pi0 is a more advanced version of smolVLA. It's also a VLA, but developed by a company called Physical Intelligence. Yeah, so smolVLA input goes to a VLM. Then VLM will tokenize it and finally pass it to a thing called action expert. So action expert is the main thing which learns, given the text and vision, what should be the action chunk. So here also it's the same concept of predicting action chunks, not a single action, but a set of future actions. So the main key algorithm or the mathematical tool used for training is called flow matching. I won't explain it in much detail, but you can go through it, search on Google what is flow matching. There are various YouTube videos also. So flow matching helps you to learn the given, learn to predict actions. So it tries to basically match to the target data set. So in your data set, you have your desired actions, and while training, it starts with a random noise, and then it tries to match using a simple concept called gradient. So it calculates the gradient and always try to get the direction or the velocity in which it should move to reduce the noise and achieve what you call low training loss. So what does training loss mean? So while training, how good your policy has achieved the dataset target action. So that is the error. So mostly, usually when you train, you might see a loss parameter, and ideally it should be around 0.02, maximum 0.03. That means your model has trained to a 97% accuracy. Yeah. So here you can see this is the commands to run the training, and there are many parameters which I guess you should explore and try. So when you have your arm assembled and you set up the LeRobot workspace, you can try first collecting data set by any of the methods. The simplest method is just the arm using leader follower setup. After you get the data set, you can use this training command where you can tweak with these parameters depending on your GPU. So batch size basically means how much batch of data is going at each time step. So for a lower GPU or a weaker GPU, you can reduce the batch size. Steps are just how much you want to train it. So here is just a simple example. So yeah, you can go through this documentation. It's always updated and it's fully open source, so people just contribute, and it's a very big community now. Then there is also a very famous model called Pi0. We won't go into much detail, but it's also a VLA. You can go through it in your free time. So this is just a VLA, but the architecture is almost similar, but the VLM used is different, and the action expert also has a different, a bit of different algorithm. Yeah, so this was all about VLA. And currently, the LeRobot also introduced a thing called World Action Model. So this is a great thing for you to explore, which is very new, and it's mostly the future of imitation learning. Yeah, and I guess that's it for the video. Yeah, thank you guys.